Okay, so any questions?
Benim var çok. Biz şimdi şey demiştik hani charge distribution bilmiyorsak bu yolla yapacağız dedik ama sonunda gelip charge distribution çıktı.
Okay, so I mean, we had claimed that eventually our aim would be to be able to study the electric and magnetic field, even if we don't know all the charge distribution. But your friend says that, so how do we use this? I mean, don't we need the charge distribution to be able to use this expression? Well, let me do a few examples. For example, let's just imagine we have a cube, a conducting cube. But we kind of isolate one of the sides. So this side is isolated from the rest. And we connect this to a battery. And let's say we ground this part. So basically we have a cube. 5 sides of the cube we fix to have a 0 potential, and the 6th side we fix to have a potential V0. Well, I don't know the charge distribution. We don't know the charge distribution. What is the charge inside this conducting cube? It's empty. Zero. And hence, the divergence of the electric field is 0 inside. Furthermore, we know the boundaries. We know E is equal to 0 or V0, depending on which side of the cube you are. No, sorry. We know that E is perpendicular to the surface. Everywhere. We don't even need to know its value. So this is our boundary condition. In the next step, we will prove that curl of E is always 0. This we will discuss on our next lecture hour on Friday. Curl of E is always 0. So we know the divergence of the electric field. We know the curl of the electric field inside our cube. We also know that it is perpendicular to the surface on the surface of the cube. That is our boundary condition. So we know the boundary condition on the cube. So we can solve for the electric field. Although we don't know the charge on the surface of the cube, by connecting it to a battery, fixing the potential here to be 0 and the potential on the outside to be V0, we are kind of putting some charges on the cube whose distribution we don't know. But nevertheless, just by using these conditions, we will solve this example. We can determine the electric field in the cube. And we can even determine the electric field outside, inside and outside, everywhere. But once we determine the electric field of the cube, well, we can calculate its divergence everywhere. So we can determine the divergence of the electric field, and this will give us the charge density on the surface of the cube. So don't read this equation from, okay, given rho, we can determine the electric field. Given the electric field, we can determine the charge density. Well, basically, that is how we are determining the charge density experimentally. We are measuring the electric field that a given charge distribution creates. By using that electric field, we are kind of trying to take its divergence, and using the divergence, we are trying to evaluate the charge density. Well, let us first write down the integral form of this Gauss law first, and then we will do some examples of both continuous charge distribution, applications of the Gauss law, etc. We have the divergence of the electric field. This is what we know. And from the divergence theorem or Stokes theorem, whichever one you would like to call it, we know that if you calculate the integral over some volume V of the divergence of any vector field, we know that this is equal to the integral of the electric field over the surface that is bounding this volume. So we have some volume. The volume there, it has a surface. So if you integrate the divergence of the electric field over that volume, then the electric field, that it should be equal to the integral of the electric field over the surface, where this ds vector, this ds is perpendicular to the surface and it is pointing outside. So the electric field integrated over this closed surface, this is equal to the divergence of the electric field, but the divergence of the electric field, we had just said it is the density over epsilon 0. Now, the boundary of any volume is a surface, but that surface is a closed surface. That is why I put this circle sign. It's a closed surface. But the integral of charge density over a volume just gives me the total charge. Of course, this is the total charge in the volume. And this is the integral form of the Gauss's law. If you consider the electric field created by any charge distribution, and that electric field, if you integrate it over a closed surface, then that integral is determined by the enclosed charge. Okay, one point that you should pay attention to here, the electric field is the electric field created by all the charges, whether it is inside the volume or outside the volume. Whereas on this side, this is only the electric field inside my volume. So here, this is the electric field created by all charges. Here on the right-hand side, we only have the charges that are inside my volume. So is the electric field on the surface 0 or not? The electric field on the surface.
Non-zero.
The electric field is non-zero. I have a charge over here. It creates an electric field. It's radially outward from the charge. So these are the electric field lines. So electric field is definitely non-zero. At every point on the surface, it's non-zero. But nevertheless, the integral of the electric field is equal to 0. Because the electric field, the charge is not inside my sphere, my volume. It's out of my volume. Well, how come it is 0? Again, the integral, whenever you say an integral, just imagine there is a summation. It's a summation. So you have this surface, you divide it into very small patches. The area of each one of the patches is equal to ds, and the normal vector is in this direction. So if you imagine a patch somewhere over here, let's say this very small patch over there, ds is somewhere in that direction. The electric field is in this direction. So the scalar product E dot ds, the contribution of E dot ds to this patch is negative. Whereas if you look at this patch over here, this is the direction of ds. Electric field is in that direction. ds is somewhat in that direction. E dot ds is positive. So here we have a negative contribution. Here we have a positive contribution to this integral. And it just turns out that when you sum them all up, the negative contributions from this side, the positive contributions from these sides, they just add up to give 0. None of those terms are 0. All of them are non-zero, but sum is 0. Yes?
Hocam sağ taraftan pozitif terimler geldi. Pardon, sol taraftan pozitif, sağ taraftan negatif terimler geldi. Bunlar birbirini götürdü. Ama sol tarafta mesafe daha uzak olduğundan dolayı elektrik alanının şiddeti daha azalmıyor. Yani sağ taraf sol tarafa göre daha yüksek bir elektrik alanına sahip. Dolayısıyla tam sıfır olmuyor gibi.
Okay. Your friend is right. You see, this point is further away. So the electric field over there is smaller. But you see, when we say the left-hand side and the right-hand side, at least in this example, it is kind of divided by these rays. In this region, E dot ds is negative. In this region, E dot ds is positive. Here, the electric field is stronger, but the surface area is smaller. Here, the electric field is smaller, but the area is larger. Here, electric field is large, area small. Here, electric field is small, area is large. So the increase in the area compensates for the decrease in the electric field. In fact, we can give it a more formal proof. If you go over your book, you will see that that is one of the proofs in your book. So let's just see, imagine two surfaces. Let's first consider the case, a charge inside my volume. Let us just take one sphere, spherical surface, inside my volume, around my charge, and some arbitrary surface. Now, this is surface 1, this is surface 2. Surface 1 is a sphere, surface 2 is an arbitrary shape. Now, what I will try to convince you, what I will try to prove is E dot ds for this point charge over S1 is equal to E dot ds over S2. You see, the areas are completely different. This S2 is at every point, it's at least almost twice or 3 times further away than S1. So the electric field on this S2 is much smaller, but the area of S2 is much larger. So do they actually exactly compensate? If the Gauss's law is true, which we had proven by using some calculus, some derivative tricks, etc., Stokes theorem, but it's not that intuitive. Can we really see it from here? Now, again, integrals equal summations. So just take your surface, divide them into very small segments. I will imagine that all these surfaces, I will divide this surface, both of them, into very, very small segments. Let me just take one of that very small segments. This is a cone, not a two-dimensional angle. It's just imagine a cone of some shape. Let's say let's look at these triangles, almost triangles. Okay, eventually I will be considering arcs. But since the angle is very small, these segments are almost straight. I mean, just always keep in mind, we will be taking these angles to be very small, almost 0. So I can just imagine this area such that this area over here is equal to this area over here. Or this volume over here is equal to this volume over here. So I can talk about some distances. Let's say this is R1. And this distance is R2. Here I have an area A1. Here I have an area A2, or DS1 and DS2. Now DS1 is proportional to R1 squared. DS2 is proportional to R2 squared. Or DS1 over DS2 is equal to R1 squared over R2 squared. This is equal to 1 over R2 squared divided by 1 over R1 squared. But that is equal to magnitude of E2 divided by magnitude of E1. So E1 times DS1 is equal to E2 times DS2. So as you have pointed out, E2 is much smaller than E1. But DS2 is much larger than DS1. Although both are infinitesimal, still this is much larger than this one in such a way that the products are the same. Exactly. They compensate each other. Well, there's still one thing left. Our surface is not DS2. Our surface is larger than DS2. Let's say this area over here, let's call it ds tilde. ds2 is equal to ds tilde times cosine of some angle. Well, that angle is this angle over there. Now, E2 times ds2 is equal to E2 times ds tilde times cosine theta. But this is equal to E2 dot ds tilde vector. Scalar product brings the cosine theta. So what this proved is that if you have an arbitrary surface, inside you have a point charge, the flux going through this arbitrary surface is equal to the flux going through this sphere that is centered at my point charge. Well, we didn't even specify what the size of this sphere is. You can just imagine it as small as you like, as long as it contains a charge. So that is what we had proven here. Now, a similar argument you can use if your surface is outside, or if your charge is outside your surface. So what we do is we just take this very thin cone, and if you like, you can just imagine such a surface, such a sphere around your charge. Well, we had proven that ds times E at this point is equal to ds times E at this point. Well, ds dot E on this patch is also equal to ds times E on this patch. But remember, here the electric field is, let's say, if this is positive charge, ds dot E is negative. Here it is positive, but their magnitudes are the same. So if you just sum these two, you get 0.
Our surface is neutral, right?
Is
Not charged. Our surface is not charged.
that surface is a mathematical surface. It doesn't even exist.
Oh, okay.
You just take an arbitrary imaginary surface. You integrate your electric field over that imaginary surface, and what you obtain is the charge. That is physical. The charge inside your volume divided by epsilon 0.
Because otherwise our electric field lines has to connect.
No, I mean, these surfaces that we are, these so-called Gaussian surfaces, as I said, they are just imaginary surfaces. They don't exist. They're just mathematical. They are things that we just imagine. Yes, question? Okay. Yes. It has to be very small. Hmm? Where? I mean, here. This one. Well, this angle can be large. This one. Now, even if it's a sphere, it will not be equal. Let's just draw the sphere. Let's draw the sphere. And the point. The right-hand side is just this segment. The left-hand side is this one. Well, this can be very far away, as you said. In that case, the left-hand side and the right-hand side will be equal. But if the point charge is, if you want the left-hand side and the right-hand side to be equal, the point charge has to be at infinity. But if it is at infinity, the electric field is 0 anyway. Well, if it is not at infinity, but very far away, in that case, the electric field at this point and the electric field at this point will be not equal or 0, but almost equal. Because the difference of the distance of this point from my charge and the distance of this point from my charge, the difference is this much. My charge is very far away, but the size is small. So the electric field here and here, they're almost same. The total area on the left-hand side and on the left and the right-hand sides, they're almost the same. And again, we will end up having E dot ds equal to 0. Let's do some examples. Let's imagine we have a rod of length L, and we would like to find the electric field. Do you like the endpoints or the middle points? Which is your favorite?
4 bölü 3. 3 bölü 4'ün
Okay, that's your homework. Okay, let's do the middle one. At a distance d, what is the electric field over there? Well, we have a continuous charge distribution. Well, let's do it formally. We already know the result. Okay, to be able to write the charge density, we should first choose some coordinate axis. So let's just, for simplicity, let's choose these coordinate axes, x, y, and z. So we are looking for the electric field at the point r is equal to dy hat. This is the point at which we are trying to evaluate the electric field. Now the problem is, what is the charge density? Well, what do we know about the charge density? First of all, if x is non-zero, it is 0. If y is non-zero, it is 0. So the charge density is definitely proportional to Dirac delta X and Dirac delta Y. Well, it can be, I mean, Z doesn't need to be 0, but Z needs to be between minus L over 2 and plus L over 2. And we can use the step function. And we can say, let's say, Z squared should be less than L squared over 4. Now, we could have written two different step functions, or we could have just said the absolute value of Z is less than L over 2, which is the same thing as Z squared is less than L squared over 4. So this should be, the charge density should be proportional to this expression. Do you agree? That it should be proportional to this one?
Anlamadım ki hocam.
Step 1.
What is the step function?
Bizi bir adım öteye taşıyan fonksiyon.
0 if x is less than 0, 1 if x is larger than 0. This is the definition of the step function. So if the argument is positive, it is 1. If it is negative, it is 0. So this function over here is 1 if z squared is less than L squared over 4. But z squared is less than L over 4 if z is between minus L over 2 and plus L over 2. So the charge density is non-zero only if z is between minus L over 2, this point, and plus L over 2, that point. And at this point, for example, if y is non-zero, there is no charge over there. At this point, there is no charge. At this point, there is no charge. The charge is only at the points x is equal to 0 and y is equal to 0. So that is why I put the Dirac deltas over there. And the step function just makes sure that it is non-zero in this interval. Of course, I can only say that this is 0 when this is 0. But that doesn't fix the proportionality constant. Let's just call that A. I don't know what A is yet. Do you agree? Disagree? Have no idea?
4pi değil mi?
We don't know. We will determine what A is.
Hocam bir daha şu Dirac deltaları anlatabilir misiniz?
So what is the charge density at x is equal to 1 meter? Well, we are given the charge distribution. We have this wire of length L. We have chosen the x-axis to lie on this rod, on this charge distribution. Origin is at the middle of this rod. So we have non-zero charge only in the segment. Everywhere else the charge is 0. So if you remember how we defined this rho of R, we said that just take a very small volume around the point R, calculate the total charge in that volume, divide by the volume. If I imagine some small volume over here, it doesn't have any charge, so rho should be 0. If I take a very small volume over here, let's say, that passes through my rod, well, no matter how small my rod is, my volume is, there's some charge on it. That means if I take the limit as the size of the volume goes to 0, it will diverge. That is what the Dirac deltas do. Of course, I still need to determine A. Yes?
X ve Y'nin sıfırdan farklı olduğu yerlerde tamam hani bizim yük yoğunluğumuz sıfır, o yüzden bu Dirac'ları kullandık da hani daha basit bir şekilde dz, zt çarpı bir constant mesela. Hani niye o şekilde çok sade bir şekilde yazmıyoruz, bu şekilde yapıyoruz?
So your proposal, rho of R is equal to
dz, z hat çarpı bir constant.
dz, z hat, this way,
Constant,
A. What is dz? Well, if you will eventually take the limit dz goes to 0, right? This is equal to 0. Plus the charge density is not itself a vector. It's a number, like 5 coulombs per meter cube. So let's just erase this one. Still, it is not true, because rho of r need not be small. You see, delta Q will be equal to rho of r times delta V. This can be very small, but that is because if we take this to be very small, but rho of r need not be small.
Hocam peki Freshman'da çözdüğünüz kısımdan farkı ne? Mesela bu problemi bu şekilde çözmüyoruz. Çok daha basit bir şekilde çözüyoruz.
Well, that is why I picked up this problem, because you already know how to solve it simply. But we will have cases where we will need to write the charge density explicitly and evaluate the electric field. So that's why I prefer to write the Dirac deltas. I mean, we will solve it that way also. Let's first solve it this way. Then we can solve it as we did in the freshman years. But you see, well, if we did everything in the way we did in the freshman years, what's the point of this course? We should take one step further, right? So this is one of our steps further. So you need to learn how to use these Dirac deltas. How to fix that A? Of course, we should be given the total charge of the rod. Let's say this is my rod. Total charge, let's call it Q. Q is equal to rho of r dx, dy, dz in Cartesian coordinates. We should integrate over all the volume. And this will tell me what A should be. So this is equal to A times dx times Dirac delta x, dy times Dirac delta y, dz times step function s squared over 4 minus z squared. And we are integrating over all of space from minus infinity to plus infinity. Well, let's start by taking the innermost integral first. Well, the step function tells me that, okay, z goes from minus infinity to infinity, but the integrand is non-zero only if z is between minus L over 2 and L over 2. Well, that integral gives me L, which I can take out of the x and y integrations. Then the y integration just gives me 1, x integration just gives me 1. So the A is nothing but Q over L. Well, in the first year, we used to call this lambda, which was linear charge density. Charge per unit length.
Kitapta bu şekilde şu anda anlatıyor. Peki hani sizin bir tavsiyeniz var mı? Başka yerlerde çalıştırırken. Çünkü kitapta da yine bu konuyu işte lambda ile tanımlayarak anlatmış mesela.
Okay, that's good enough. No? Do your homework that you will have for the weekend, where you will be writing down the charge densities for various charge distributions. and go back to Ohanian or your first year physics book. So now we know the charge density. This is this is not the linear charge density, this is the volume charge density. In fact, that is why we have all these Dirac deltas, relating the linear charge density to the volume charge density. Now, basically, we are done. We know the charge density. We know the expression for the electric field. In fact, this electric field, we can, I mean, if you can evaluate that integral, we know the electric field at every point, not just a single point. So let's write it down. So the electric field, this is the total electric field, is equal to dx from minus infinity to infinity, dy from minus infinity to infinity, dz from minus infinity to infinity of our charge density, well, let's say x prime, y prime, z prime. Charge density is Q over L, Dirac delta of x prime, Dirac delta of y prime, Dirac delta of, no, not Dirac delta, theta of L squared over 4 minus z squared of r minus r prime divided by r minus r prime cubed. As I said, the rest is algebra. Well, let's do that algebra, at least for this case. Here we have the r prime vector is x in the x prime in the x hat plus y prime in the y hat plus z prime in the z hat. R vector was d in the y hat. You see here r vector is d in the y hat. This is not dy hat. It's just d is the number. It's not the differential of y hat. D is the number multiplied by y hat. Now first let's calculate what is r minus r prime magnitude. Now r minus r prime vector is x prime in the x hat plus y prime minus d, no, sorry. Minus x prime in the x hat plus d minus y prime in the y hat plus or minus z prime in the z hat. So the length of this vector is equal to x prime squared plus d minus y prime squared plus z prime squared, all square root. Now let's put everything back. Well, but in putting everything back, I will take the x and y, x prime and y prime integrals, because there are already these Dirac delta functions, x prime and y prime. These Dirac deltas just tell me that whenever I see an x prime, I should put 0. Whenever I see a y prime, I should put 0 in my integrand. Furthermore, this step function tells me that z prime integral doesn't go from minus infinity to infinity, but only from minus L over 2 to plus L over 2. So the electric field is equal to Q over L times integral over dz prime from minus L over 2 to plus L over 2. And r minus r prime vector I had evaluated over here. But remember, r minus r prime vector in x prime and y prime, I should just put 0. What remains is d in the y hat minus z prime in the z hat. This is the r minus r prime vector when I put x prime and y prime equal to 0, divided by d minus d squared plus z prime squared to the power 3 halves. I can divide this into two. This will be equal to Q over L from minus L over 2 to plus L over 2 dz prime in the dy hat direction of 1 over d squared plus z prime squared to the power 3 halves. This is one term. Minus Q over L in the z hat direction dz prime from minus L over 2 to plus L over 2 times z prime divided by d squared plus z prime squared raised to the power 3 halves. So for example, if we wanted to follow his claim, his proposition, that we should maybe put this charge, calculate the electric field not at the middle, but at 3/4. So what would have changed? Well, I would still choose my y-axis to pass through my point D over here, but the integration variable will be from minus L over 4 to 3L over 4, not from minus L over 2 to 3L over 2. The step function, it would probably be simpler to write two step functions to show it explicitly. And then if you change that limit, the integrals over here would get a bit more complicated, not much, but just a bit. In any case, you have to evaluate this integral. You cannot avoid it. But if you look at this function, well, this function is what we call an odd function. So if you just plot that function, let's say, so this is z prime over d squared plus z prime squared to the power 3 halves. It looks something like this one. Nope. Okay, not that. It looks something like this. It's an odd function, and we are integrating it from minus L over 2 to plus L over 2. But this area over here, since it's an odd function, is equal to this area over here. But one is negative, one is positive, so when you sum them up, the result is 0. This integral is 0. That's why I prefer to put it in the middle. At least now we only need to evaluate one integral. So the electric field at the point we have chosen is equal to QD over L in the y hat direction times this integral. This is not the easiest way to evaluate this electric field. As your friend has pointed out, in freshman we did it in easier ways, not like this. But you see, if we have a more complicated charge distribution, you will not be able to evaluate it in the means that we used to do it in your freshman years. But this derivation will not get more complicated than this one, maybe slightly more. The integrals will be a bit more complicated if you have a more complicated charge distribution, but nevertheless the steps that you need to carry out until you reach a point where you can just tell the computer to do will be more or less the same. It will not change. So I agree, in simple problems, this is a complicated way of evaluating it, but the complications in this method doesn't change whether your charge distribution is simple in this one, like this one, or more complicated.
Z prime nereden geldi?
Well, our definition of the electric field. You see, hope this is Z prime. If you look at the general expression of our electric field, it's an integral over the volume of the charge density, and here we have r minus r prime. Z prime is the coordinate of r prime. And we are integrating over R prime. R is the point at which we are trying to figure out the electric field. Okay, as I checked this morning, there were 6 students who were asking for a recitation. I don't know if the number has increased, so we will have recitation tomorrow morning. Assuming that there will be at least 5 students that show up among that 6. Yes, any last minute questions? Well, the recitation hour, it depends on you. If the students who show up, you want to have the material repeated, we can repeat it. If you have questions, some example questions that you want to be discussed in the recitation hour, we can discuss it. If you don't bring anything, I will just make up some questions and we can go over questions. There is one more question. Go up or down? Any other questions? Then you can go. See you tomorrow or on Friday.